Okay, so this is kind of a reiteration of something that Dave Page, actually, and others were talking about earlier today. So I'll try and get through it real quickly, but it's sort of focused on the question of why aren't, or what is the evidence for ice in places where ice could be sequestered, as indicated by the diviner temperature maps and modeling. As we've seen from Dave and others, there is a very large area outside of even permanently shadowed regions where subsurface ice stability it can be pretty well assured. Temperatures are low enough for ice stability over very, very long periods of time, at least a billion years. And people have noticed that there's some similarity between the maps, sorry about that, maps of the neutron suppression or decreases in epithermal neutron count rate and these areas of subsurface ice stability. And so the question is, is that really indicating that those locations really have ice in them? And if so, how much and how is it distributed and stuff? So what we're going to do is actually put ice in these locations at the depth that it's allowed at certain prescribed percentages and ask the question, does it look like what we actually measure from orbit? And then taking the results of that, explore what the ramifications are for the distribution of buried ice. So here's a temperature map that kind of like what Dave was showing. This is average surface temperature. It's a model that Page and Company published in 2010. And on the right is what would happen if you took that map and just, without considering anything else, just convolved it with the instrument response function for the Lunar Prospector neutron spectrometer, and you can see something that, lo and behold, looks like it's got a sort of a low up here, pretty close to the pole, but out traversing the three big craters, Hayworth, Shoemaker, and Faustini. And then, of course, there's Cabeus over here, which is a sort of separate cold area, as you can see on the higher resolution map. So this is the fuzzed out version that you would see if the neutron spectrometer on Prospector was able to see this map from orbit. And let's compare it now to the actual Prospector map shown on the left. So this is neutron count rate in the epithermal energy range. And you can see Cabeus is a great big sort of hole in the count rate over here. I say great big hole, but it's really just a 10% reduction or so in count rate over what is dry material out here further away from the pole. Here's Shoemaker crater right here. You can see that there's some similarities but also some differences. There are places just where you see reductions that aren't present in the temperature map. So now looking at the higher resolution North Pole and South Pole depth to stable ice that Dave and the team put together in 2010, you can see there's the white areas here are permanently shadow locations, generally within craters near the pole. And the red areas going up to sort of roughly orangish yellow are depths to stable, the stable ice condition of about 0 to 30 centimeters. So this is in meters over here. And you can see most of the terrain here is actually, the stable regions are stable within a very short distance of the lunar surface. And so if you do a histogram of that, you find that in these maps, most of this is just a histogram for what is deeper than 1.5 meters, and most of what you're looking at here has ice or permafrost depths, if you like, of less than 50 centimeters depth. And the reason I bring that up is kind of shown in the next slide here. This is this shows how epithermal count rate seen by whatever neutron spectrometer would change as a function of burial depth if you had icy material of this amount of water ice in it, 1 weight percent, 10 weight percent, 0.1 weight percent, and so forth, against burial depth, and this is the count rate given in the color scale over here. So you can see in the top about 40 or so centimeters of depth, things don't change very much. What that means is that even if you have icy materials, up to about 10 weight percent or so, within 40 centimeters of the surface, you're going to see basically the same sort of signature that you would see if it was fairly close to the surface. That's not the case if the water ice is actually buried at a meter or so. The instruments become less sensitive to that, and you can see very little contrast then between something that's really dry and something that has ice but a meter or so down. So this is the muting effect that you would expect to see by burying ice, icy materials at greater depths than, say, about 90 centimeters or so. There's an effect, but it's a small one. So just to put things in perspective, remember what L-Cross got. Tony quoted 5.6 plus or minus 2.9 8% H2O based on the observed ejecta that L-Cross saw. And then there are other hydrogenous species that they identified and made use of to create spectrum, spectral fit that you see here. And they amount to about 1.8 weight% of water equivalent hydrogen. They were not water, they were other things, of course, things like CH3, OH, and so forth. So the range of possible water abundances we're talking about in the regolith that L-Cross impacted into is between 3 and 10 weight% or so. Tony separately got a depth estimate of 0.7 meters or so depth of burial, so that would indicate that you might begin to see some of this muting effect. But the question is, what would happen if you actually take abundances less than that and place them in the lunar, in locations where and depths where water ice would be stable, and that's what's shown here on the left. So this is the same map as ice stability map, but now we've actually created what the epithermal neutron flux would be out of those locations, assuming 1 weight% of water equivalent hydrogen in the material fairly close to the surface, within 30 centimeters or so of the surface. So this is a fairly significant abundance, but it's less than that of the lunar L-Cross results. And if you compare that, actually this is the high resolution version, and this is what you would get if you convolved the instrument response function with this predicted map, and then say what would I see from orbit using the Prospector neutron spectrometer for 1 weight% water equivalent hydrogen. The first thing to notice is that the drop in epithermal neutron flux is very substantial. It goes from 20 counts per second out here in the drier regions to 15 counts per second, and any of you who are familiar with the Prospector data will know that this is a much larger drop in epithermal neutron flux than is actually measured. And in fact, if you put the neutron data on the same scale, the same color scale, you barely see anything in the data. So obviously what this means is that if you put 1 weight% there, that's way more than actually what we would be seeing here. So right away you know that cold traps, subsurface cold traps, are not the answer to the question of where is the water ice. It's clearly some subset of where ice can be stable. So we know that right away. This just reinforces that fact. Scatter plot, assuming 1 weight% between the binned lunar Prospector data and the predicted data that Prospector would have seen had it been 1 weight% in the subsurface cold traps. And it's more like you get a slightly better correlation, but really not great, and it's because the spatial distributions really are different. This is 0.3 weight%, so it's more consistent, but it's still not consistent with the L-Cross results. Here's the North Pole. Got to do the same thing for both poles, and so you can see here it's really clear that the distribution of hydrogen as seen by the neutron spectrometer is very different from what would be predicted from a 1 weight% distribution in the page at our subsurface cold traps. And so this is the prediction. This is what is actually observed. Again, a very large decrease predicted and a very small decrease actually observed by the spacecraft. So I'm not going to dwell too much on this. Norbert talked about the results of cometary impact, and so one of the things that sort of want to think about is if H2O and or OH is migrating around on the surface, ballistically hopping, and eventually finding its way into the cold traps at the poles, one would expect this to be kind of a gentle rain of molecules down into the cold traps, and it would pretty much make them all equally filled if this were the primary mechanism for placing water and other hydrogenous volatiles in those locations. You'd pretty much see a uniform and homogeneous distribution, absent any other processes that are going to create inhomogeneous distributions. And to first order, that's probably true for comets as well, though Norbert, I know, has looked at the asymmetry in cometary debris and where the fallout would land, and how that might actually populate cold traps differently as a function of location. Anyway, to wrap up, at least for the cases we were just talking about, homogeneous sources such as steadily infalling molecular species would tend to populate all the cold traps equally, and therefore they'd have the same amount going from crater to crater, and that's not what we see. A cometary impact might provide inhomogeneous distribution, again, because thinking about now what Norbert was talking about earlier. And in any case, the data are inconsistent with a one-way percent, let alone L-cross abundances, starting at as shallow as the permafrost depth. So because this produces a much, much more significant and dramatic signature than we actually observe from orbit. The data are consistent with a range of abundance and burial depths, which is kind of our way out. There is apparently an inhomogeneous distribution. Some cold traps are populated, some are not. That's actually something we found, we postulated with earlier observations as well with the prospectors. But it also is consistent with the possibility that the L-cross abundances do exist at those locations, but at greater than 1 meter depth, or about 1 meter depth or so, because that mutes the signature that one would see from orbit. There's also the possibility that the inhomogeneity scales go right down to the scales that of a few meters or so because of impact processes since the last time that ice was emplaced. And so without Dana's permission, I'm including this thing that she had in her poster a little more than a year ago. This kind of illustrates how disruptive the impact process and redistribution processes are, and how it can disrupt an ice-bearing surface and what you'd end up with at fairly small scales. This is 20 meters on a side, and so this kind of result is what we might expect to see in permanently shadowed areas, and even in locations that receive low-angle oblique sun for a few days out of the month and only at solstice, so that the subsurface is really a good ice repository, but it can't resist the effects of impacts, and this is sort of the structure you would end up with in that case. So thanks, everybody.
All right, looks like we got a question from Paul Hain. Rick, is there any asymmetry in the moon's interaction with Earth's magnetosphere that could lead to the observed H asymmetry?
Well, one possibility that kind of comes to mind is that when the moon is in the magnetotail, that's around the full moon phase, some materials from the upper atmosphere, actually ions from the upper atmosphere, colder ions flowing out of the auroral regions, could potentially reach the moon. They would basically bathe the entire lunar surface with them, but the place that they'd get stuck longest, obviously, would be in the cold traps. Once those ions would arrive at the surface, they'd neutralize out on hitting the surface, and there they would sit. Those are things like hydrogen and oxygen flowing out of the Earth's ionosphere. So that's one possibility that might create some degree of anisotropy in the distribution, but the maps don't really reflect that. In other words, you'd expect to see perhaps near side features more strongly populated by that effect than far side features, and that's not the asymmetry or the inhomogeneity that we see, in my opinion. Does that answer your question, Paul?
Yeah, thanks.